Alright, and the stream has begun. Okay, hello fellas. Time to just start posting the stream everywhere while I wait for a few viewers. Is the internet a little slow today? I feel like it is a little slow. I hope it doesn't interfere with the stream too much. This a little slower internet. Anyway, alright, just gonna post the stream like literally everywhere. Copy, paste. Alright. Hello. Welcome y'all. Welcome to the stream. So today the problems today is actually about, give me a moment, give me a moment. So the problems today is about projectile motion with air resistance. And guess what? Guess who did projectile motion in Minecraft with air resistance? Me. All right. I gotta post this somewhere. What do I caption it? In projectile motion with drag force for my homework problems. Alright, and copy paste that. Gonna tweet that out. So yeah, welcome to Game Theory. Okay, is chat working? Give me a sec. Well, my internet is not very optimal up here. So yeah, you might be hearing a little slight difference in acoustic in this on this stream. I've been trying to like find some spot where I could stream comfortably. Very optimal up here. So yeah, because of the fact that if I stream downstairs, Mom's gonna be home at any moment, and should pop into my stream. Hello, welcome to the stream, Frost. All right, that's been posted. I gotta put this like literally everywhere. Do I have it? I do have it. All right, I gotta post this here. And then we'll start because we'll start in a bit. Oh, I didn't realize my friend actually did a Minecraft video. Alright, let me just paste my link everywhere first. How delayed is the stream, guys? How delayed is it? Because it's looking like it is quite delayed. Hello Mike, welcome to stream. Drop frame detected. What's the problem? Check the health of your internet connection. Oh shoot. Hello Mike, I do remember you. Howdy, how have you been? Why is it? Why? Wait. Is my stream? Chat, is my stream alright? How are you? It's been a long time no see. It's been great. I've been doing pretty well in college. Why is my stream not working on my phone? I hope it's working everywhere else. Is it working on my phone? Oh shoot, okay. No, it looks like it's not working actually. Never mind, it is. Are you gonna work or not? Okay, yeah, might have to get that fixed. I might have to get my internet fixed. For now, though, let me just paste this in a few more servers. I don't think they'd mind me posting my homework over here in this channel. I think I posted this almost everywhere. Right, this channel, this server, and we'll get started. All right. Okay. It's wow. That is a lot of drop frames. Hello, welcome to the stream, Konami. The bitrate is all. Wait, I can lower the bitrate. Wait, chat. Let me try something. Can I lower it? Like on stream? Did that work? Did I lower the bitrate on stream? Or is it me, or did something happen to the stream? Well, shoot. Is it okay? Guys, oh my god, that is terrible. Okay. Bitrate, it is back to normal. I have to find a way to now. I might hop to a different Wi-Fi. Can I use this Wi-Fi? Give me a sec, guys. I might get disconnected for a few seconds. Let's see. Never mind. I don't remember the password. Go fix your computer. It's not my computer. It's my internet. The internet up here is kind of ass. So give me a moment. Drop frames detected. 38% of this. Holy shit. Some frames have not been uploaded. This problem is usually related to a poor network connection. She physics on my homework, China. Okay, I'm gonna be right back, guys. I'm gonna go change to a different Wi-Fi real quick, but I forgot the Wi-Fi password, so I'm gonna go ask my dad. I'll be back. You guys can chat in chat. Give me like 2-3 minutes. I don't know. Yeah. Dad! Alright, chat, I got the password. I hope this works. Because it better. Does it work? Your stream is quiet. Yeah, I wasn't talking. Because I was getting the Wi-Fi password. Because it should be working well now. At least decently. Somewhat. Is it good? Is it real time? Let me draw something so you guys can see if it is real time. So I can also see it because so I know that the image doesn't just suddenly show up on the stream. Is it working well? Yes, perfect. All right, we can start. Okay, so I'll be connecting to this Wi-Fi from now on when I stream. Because right now upstairs, in a different room from the previous ones, because, again, I don't want to, what the fuck did I just do? I know what I just did, I just don't know why I did it. Okay. Alright, so we're gonna be doing a few homework problems today. 2, to be precise. Obviously, these 2 problems will we have more other sub questions, but you get it. Here's the first question, which is a little lengthy because it is divided into how many parts? A, B, and C. Yeah. So the thing is, today's subject was classical mechanics. Yeah, today's subject was classical mechanics, and it's about projectile motion with air resistance. Now take a guess who made two videos regarding projectile motion with air resistance in Minecraft. Yup, it's me. Alright, so, drop frame still detected somehow. Probably because I haven't changed the Wi-Fi for that long. I think it should get better eventually. It shouldn't be dropped like that anymore. Or at most it's gonna drop like not too much. It's not gonna drop very much. Alright. Consider an object that is thrown vertically. Mr. Beast, yeah. Okay. Consider an object that's thrown vertically with an initial speed v0 in a linear medium. What it means by a linear medium is that the air resistance it's not white, okay. Linear medium means that the air resistance is linear. Here it means that the drag force is directly proportional to v, the velocity of the projectile. All right. So you know where else is a linear medium? The air in Minecraft. Yeah, I'm linking everything to Minecraft here because I'm proud of this, okay? I studied this since I was like in high school. So obviously I have a little bit of an ego boost here when I enter this classroom and learn that I would be studying this topic. Okay. So if I got kidnapped here. Welcome to the stream. You can't escape. So let's first do section A. Section A, measuring y upwards from the point of release. Write expressions for the object's velocity vy as a function of time, and then find the position as a function of time. So basically, this is thrown vertically up. So obviously, there's going to be v0 there. And it's going to be thrown vertically, so that means the axis up here is going to be y. And this is going to be a time axis. The trajectory should be something like, I don't know, probably something like that. We'll figure it out. Oh, hey, you're back. Yep, I'm back. I escaped, no one saw me. Yeah, I'm back. Had to change the Wi-Fi a little bit. So obviously, when we look at the object, we are gonna see that there's gonna be a drag force F here, and there's gonna be the other force, the weight of the object, mg. So the total force, this drag force is gonna be I'm gonna call it kv. No, beta v. Because so as to make it parallel. Anywho, how are things, man? Long time no see. Yeah, I've been having fun in university. Things are actually a little more challenging now. I'm gonna call this drag force BMV, where beta m, where beta is some constant, so that we would be able to get the so that we could write the total force. Sorry. F is going to be negative mg. That's nice. Indeed it is. How about you? How have you been, Mike? Alright. This is the force acting on the object. it's negative mg, negative beta mv. So if v is going up, which means v is positive, this whole term is going to be negative, which means that the force is pulling it down. On the other hand, if v is negative, it means that this whole term is going to be positive. And when that whole term is positive, it means that the force is pulling up because it's resisting the motion of the object. Now, of course, we write down Newton's law, which is F equals ma. In our case, F is going to be equal to m. A is going to be, A is the acceleration, so the acceleration is going to be equal to the time derivative of the velocity. And we set this to be equal to negative mg minus beta mv from the force. So now we can set up this equation. You guys know how to do this. If you don't, go watch my video. I should have the. If you don't, go watch my videos. You should watch it. It's a good video. I think it's. There's one video. I was not supposed to put it like that. Oh, I have to. Hold on, I have to copy the video. Boop. Copy the thumbnail, paste it on a new layer. Keep canvas size, and yeah. You guys should go watch this video. I put the thumbnail in the thumbnail as well. It's a thumbnail section. So we have this projectile motion. It's gonna help you catch up on this video, on this stream. Or, well, honestly, this whole video is sufficient to as a replacement for the stream, because, well, it's literally the whole subject. The whole subject is like studying about the projectile motion with drag force. So obviously, I'll be able to answer a lot of questions. I'm sorry, my ego is getting the best of me. All right. So now we write this down: dv by dt equals to negative mg. So now we cancel out the m's. So we have negative g, negative b, negative beta v. Now in my video I put g here as positive, but the value of g itself is negative. In our case, I'll just make sure g is positive and we put in the negative sign in front of it. It doesn't really matter. Yeah, it's just a few signs that are swapped around. Shouldn't be too big of a problem. I don't want it to be confusing though, but so just I'll let you know that. So we have negative g minus beta v dv equals to dt. This is known as a separable differential equation. I also elucidated on this in the, did I use that word right? Whatever. This equation, I explained this in my video as well. These are called separable differential equation. On the left hand side, everything is just in terms of v. On the right hand side, everything is in terms of t. So now we can integrate both sides of the equation. Here we start off with v. We start with v equals v naught, and then we go to v at any arbitrary point in time. On the other hand, on this side, we start off at time equals 0, and then we get to any point in time, t. Which we can now solve the equation. On this side, it's going to be, I'll perform the integration in my head. It's going to end up being negative 1 over beta times the natural log of minus g minus beta v. Wait a fucking minute. It shouldn't. Oh, never mind. Yeah, it makes sense. It makes sense. Wait a minute. No, we don't have. Nothing. I'm just tripping. Sorry. And we divide that by g minus beta v naught. I perform this integration some time ago. I already know the answer to it because, well, I did it in my channel. Yeah, obviously I'll be selling out my channel. Obviously I would. It's my stream. I can do whatever I want. You guys hit subscribe, okay? Okay, so now I bring this over to the other side. We get we're gonna end up with natural log of negative g minus beta v divided by negative g minus beta v naught. Boop. And it's going to be equal to negative beta t. So now we have a natural log of that. We exponentiate both sides of the equation. So we're going to get negative g minus beta v equals to negative g minus beta v naught. Times e to the negative beta t, and that is our okay, we're not there yet, just give me a sec. So we're gonna have negative beta v equals to negative g plus beta v naught. I'm factoring out the negative 1. There's going to be e to the negative beta t, and then there's going to be plus g. Okay. This is just solving a differential equation. It shouldn't be too bad. I think it's understandable somewhat. If you go watch that video, you would probably be able to catch up. If you haven't, do it after the stream, okay? Because I actually go much more in depth in that video. I think I did pretty well explaining in that video. Anyway, v equals to, so now we're going to be able to write it as v equals to negative, no longer negative. It's going to be g over beta, because I'm moving negative beta over to this side. It's going to be g over beta plus v naught times e to negative beta t plus g over beta. Okay. So now let's interpret this this equation. What does this equation mean? And I'm using this exact same visual as I did in that video. Whoop. All right. So first of all, we have g. First of all, we have this term g over beta. So if if time goes to infinity, this entire term goes to 0, and when this entire term goes to 0, it takes this whole term along with it. So we're going to be left with g over beta. And that's going to be this value, and it's going to be this value over here. Now this term, whatever it is, what matters is that whatever v is, whatever v naught starts with, so v naught could be over here, it will exponentially goes into this g over beta. No matter where we start off, v naught, no matter what v naught is, if we start over here, it's gonna approach it's gonna approach this guy. If we start down here, it's gonna approach this guy. I think I did something wrong. Yeah, I did. Oh, I did something a little wrong. This is supposed to be negative g because I'm bringing negative beta over to this side. Yo, what the heck is this? Hello, Sus. Hello. Hey. I'm not quite sure why my phone is not showing all the messages. Hello, welcome to the stream. Oh, there we go. Yo, what the hell is this? Welcome to my homework stream. This is actually the exact same homework. Whatever, I guess I'll continue my discrete math. Ah, right. You have to learn engineering. You have to study discrete math, right? Have fun with that. Have you been writing proofs? Have you been writing proofs, or is that like a different year, or are you actually writing proofs? Right. Actually, discrete math is literally all about writing proofs. What am I saying? What am I saying? I should delete that. Okay, so this actually means that sure. All right. So yeah, this is projectile motion with linear drag. You are actually the one who got me into this whole thing, like the projectile with air resistance. So you were the one who got me into this whole thing. Remember when we playing when we were playing with command blocks back during COVID? Yeah, and then we did the and we used the command block to like track the arrow. Yeah, that was that. Yeah, and then it tracked out, and turns out that it's actually not parabolic, where it turns out that it's actually like a little bit more. It's slower on this side. Yeah, that was the session that started all of this. I blame everything on you. Yeah. All right, and this will. So this graph V is going to be negative g over beta, wherever, it depends on what V naught is. V naught is going to be the one over here. So if V naught is over here, it's going to decay down, and as time goes on, it's going to approach this velocity. Bro, why me? I don't know, you just happen to be the one playing at that time. So yeah, no matter what your velocity is, if your velocity exceeds that, it's gonna go back to this thing. So this thing is called the terminal velocity, which this thing is called the terminal velocity. I'm gonna denote it V with actually they said it in the VTER. So I'm just gonna call it VT, V subscript T. So we're gonna have V subscript T plus V naught e to the negative beta T minus Vt. And this is velocity as a function of time. So again, interpreting the whole thing, if we interpret the equation, we know that if t equals 0, this term becomes 1. So we're going to end up with Vt plus V naught minus Vt. So we're going to end up with just V naught. If this term goes to infinity, this whole thing goes to 0. This whole thing goes to 0, so we're going to be left with negative Vt, which means that it's going to achieve terminal velocity as it goes downwards. So that is our first half of question A. Find the time for the object to reach its height. Actually, no, we need the position as well. So let's do that. To get the position, we're going to be integrating this function again, which is pretty easy. So I'm just going to go ahead and skip it. Yeah. So I'm going to integrate Vt starting from time 0 to time whatever t is. Yeah. Which we're gonna get Vt plus V naught times e to the negative beta t minus 1 subtracted by Vt times t, and I completely forgot about this factor 1 over beta, minus 1 over beta right there from the integration. This part is the integration part. You probably have learned this already, I hope you guys have learned this. Anyway, this is our expression for the y-axis. This is where the object will be after a certain time of t has passed. which again you already. Wait a fucking minute. Am I missing something? No. Hello, Fox. Welcome to the stream. Wait, wrong account. Okay, get on your main. Get on your main. So there's VT. I integrate the whole. I integrate the whole thing. Obviously, there's gonna be plus V plus Y naught here, but I set this guy to be 0. That's gonna be the initial position in the y-axis. I set it to be 0. We are gonna end up with this, and this is our answer. Let me just rewrite it. So y equals to -1 over beta Vt plus V naught times e to negative beta t minus 1 minus Vt times t. And this is our answer for part A. Sorry if I'm talking like not talking as much. What the fuck? Okay. Sorry if I'm not talking as much as I usually do. I'm just a little bit sleepy today. And also there's like not much going on in chat either, so there's nothing to talk about. What do you guys want to talk about while I think about how to approach the next question? Find the time for the object to reach its highest point at its position. Okay. Alright, too late. You guys responded too late. I'm starting the next question now. So we have to find where the object reaches its climax. Up here, and obviously up here, v along the y-axis must be equal to 0. I'm gonna reduce the brush size. So obviously the upwards trip is gonna be vy equals 0. No, at the peak, the velocity at the peak must be equal to 0. And because we already know what is the velocity, we can just set all of this to be equal to 0. That is, v as a function of time is equal to v naught plus vt e to negative beta t minus vt. So we set this thing to be equal to 0, which is where the maximum value is, where the highest point is. This time t max here are in the right countdown. Hello, Azazel. Welcome to the stream. So I'm doing a question on projectile motion. Yeah, projectile motion with this projectile motion has air resistance added to it. I actually covered this whole thing in a YouTube video of mine. You could check it out. Obviously, alright, chat. If someone new joins, I will always have to sell out. I made this one video on projectile motion, which is exactly what this question is about. So I'm going a little quickly here because, well, I've been through this. I'm quite experienced with this kind of problem. So yeah, we have this. Bro, I slept through my physics class. Don't worry, me too. So basically, this is gonna be, so we got this equation, which is the time, which is the velocity along the y-axis at time t. Because if we want t max, so here is gonna be the t max. Here is the point, is the time where the object has reached its peak. So the t max here, we're gonna have the fact that v is the velocity is no longer going upwards. It's no longer going upwards, so it must be set to 0. If it starts going downwards, then it's not going to be at the highest point anymore. So this value must not be negative either. It shouldn't be positive, because if it's positive, then it can continue moving upwards even more, which means it's not at the highest point. If it's negative, that means it had already been going downwards, so that means it's not the highest point. So the highest point is when v here must be equal to 0. 0 is going to be equal to the initial velocity plus the terminal velocity times e. Oh wait, why does the emoji didn't work on the chat overlay thing? That's weird. That is really that's a bro moment. How would I even make it work? Whatever, you guys can imagine it work, because I'm pretty sure you can like see it in the live chat as well. I have both the stream overlay thing on and the live chat thing on simultaneously, so I will be able to see both. Although for some reason it would sometimes not show some messages in the live chat. Unrelated, but how do you feel about system dying? He's not dead. Come on. He's probably just white for a brief moment. Come on. He's gonna be back like next week. Right? I'm coping. Yeah. So this is equal to holy cope. We gotta kill Thorn. Alright, so this exponential function is going to be equivalent to this, which means that e to beta t is equal to v0 plus vt divided by vt. Therefore, no, don't kill. Just please look. So for those unaware, there's been an ARG going on Twitter. Oh, well, I actually understand what you're talking about. Nice. So for those unaware, there's like an ARG running on Twitter that I've been watching consistently, and it's been through some crazy arcs. It's literally today, like crazy shit happened. So now we have e to the beta t. If we take the natural log of the entire function, of the entire equation, we're going to have natural log of e to the beta t is equal to the natural log of this whole thing, which this whole thing I'm going to abbreviate, not really abbreviate, simplify to this. Because vt here, this term cancel out, it becomes 1, this term becomes this term. And then we take the natural log of the entire thing. We know that the natural log of e to the something is going to be equal to that thing. And on the right hand side it's still the same. Okay, so therefore this is the t max, the time at which the object is at its peak. So Tmax equals to 1 over beta natural log of 1 plus v0 over vt. Boop. And we're almost done. Not yet. We're not done yet, but like we need to find it. Oh, never mind. Oh yes, we do have to find the positions as well. Okay, so we have Tmax, the time at the peak. The time since the beginning to where it hits the peak, the highest point. Yeah, and then we also know from the previous part that y equals to this whole thing. So I'm just gonna go ahead and try to copy that. We're gonna get y equals to. I'm gonna change. Not really change. I'm going to distribute negative over here into this term. So it becomes 1 minus e to negative beta t instead. So it'll be a little easier without the negative signs everywhere. Vt plus v0 1 minus e to negative beta t. And then with minus vt. And now what we gotta do is we just plug this term in. If we want y max, we're gonna have to plug in t max. So hold on, let me just max. Just think of that as max. I don't have enough pixels. Max. Okay. So we're gonna have 1 over beta vt plus v naught 1 minus e to the negative beta t max. T max is 1 over beta, so the betas cancel out. Cool, you lost me like a few minutes ago. Well, what I personally would do is just black box some of the equations. Like, most of the equations look a little messy, so I don't really think of them. I just think of them as one thing to just plug them in. I already interpreted what they mean previously, but when I'm missing something, like where did this equation come from, I typically just black box it and just think of it as what it does first, and then just follow along. How it came to be is something that I would come back to catch up later on when that happens, when I get lost. That's what I would do. So anyway, T max here. So this whole thing, you're very smart. Thank you, I agree. This become negative natural log of 1 plus v naught over vt. Subtracted by that, divided by t, and then we have natural log of 1 plus v naught over vt. Okay, now what? Now it's trying to simplify a little bit. 1 over beta, this thing stays pretty much the same. 1 here is just going to be there. And then e to the negative natural log of this thing is going to be equal to 1 over this thing. Because negative natural log okay, wait. Because there's this property of a logarithm, basically negative log x. Wait, have you eaten yet? No, I actually plan to eat like after this stream. Which is like, it shouldn't be too long. It's just it's just this question and then the next one. The next one's just a simple, let me check. Yeah, the next one is just a simple differential equation. I think I got it. I think I can do it in like no time. So like, don't worry about it. I'll be fine. This stream probably won't go as long as last time, where I actually kind of struggled with the question. Trust me, I'll be fine. I'm actually starting to get a little hungry. Alright. So, if we exponentiate this whole thing, e to the power of this whole thing, it's going to be equal to e to this whole thing, e to the power of this whole thing, and it's going to be equal to 1 over x. So the same applies to this one. It's going to be 1 over this thing, which we can now solve by doing a little bit of algebra. It shouldn't be too big of a pain. This becomes vt, I think, and this becomes vt plus v naught. So this thing's, so 1 minus that is going to be vt plus v naught. Subtract, yep, and then this one is going to be, oh, I'm allergic to algebra. It is a pain. Gonna be real, algebra is kind of boring. And it's like, there's so much you have to keep track of that it's kind of a pain. And it's kind of boring. Like, personally, I like calculus better because it's a bit of algebra, but like the main meat of it is actually a little more fun than like algebra, having to like move. Algebra, you have to like multiply variables and shit. and like you have to factor out terms. All of those is kind of boring to me, so I don't really enjoy it much. VT here cancels out. This term cancels out. Oh yeah, I think I like calculus a little better. Yeah, calculus is actually fun if you know what you're doing. It's very fun, actually. Because, well, it is. It has a lot of practical uses that obviously a lot normal people wouldn't think of it. Yeah, mostly because our teachers allow us to keep index cards with formulas. Yeah, I feel like at some point you shouldn't be remembering formulas, but rather you should be understanding the techniques for like differentiation or integrations. Like as you go higher in the mathematics, you start to have to rely less on identities or memorization, and you would have to be much better at understanding what the fuck is going on. Which unfortunately is not the case in high school, so a lot of people would get fucked over by that. Okay, yeah, I think that's it. This is the final answer to question B. Truth nuke, yeah. Find time for the object to reach a science point and find the y max at that point. Yep, this is the value of y max. Alright, that's simple enough. Kind of. It's just algebra. It's just a lot of algebra. So nothing too interesting to be talked about, I guess. The meaning is quite interesting, of course. Like this is the highest point, the point where the object stops going up and starts to fall back down. Yeah, it's the highest point. So y max is gonna be equal to that. Okay, now this is a little bit of a trick. Question C. Show that as the drag coefficient approaches 0, your last answer reduces to the well-known result y max equals to 1/2 v0 squared over g for an object in a vacuum. So in regular projectile motion, what we have is we just have a simple projectile, right? We just have a simple projectile. We have v naught y. In a case where it's not a projectile motion, all right, just for an easier case, just throwing something directly upwards in a vacuum with no air resistance. If you throw it upwards at v naught, the highest point here is going to be equal to v naught squared over 2g. This is a well-known, well, maybe not well-known, but like you can prove this using like there are multiple ways you can prove this. There's conservation of energy. There's the just the linear motion formula where we have v squared equals to u squared plus 2ah, which can bring us to the fact that h here is equal to v naught squared over 2g. This is in the vacuum, which obviously is not the case here, because in our case we do have to consider the air resistance now. So yeah, this does in fact burst your bubble. If this in fact bursts your bubble a little bit, us physicists do actually consider air resistance, although it's a rare case, but yeah, that happens. So we had y max here was equal to v naught over beta, I think. V naught over beta subtracted by vt times the natural log of that. Vt over beta times the natural log. Oh gosh, I almost missed another stream. Hello, welcome to the stream. You may have missed like the first half of the stream. I was watching an Indonesian movie. So like this stream, basically, hello, how do I actually pronounce your name? Sirawakalong? I hope I did that. I hope I pronounced it right. So yeah, this is okay, what was I saying? Wait, hold on, I'm short-circuiting. Alright, this whole thing, if you guys missed my first half of the stream, you can go watch my, you're still on my hit list. What hit list are you guys talking about? So you guys can go watch my projectile motion video. It's like, I think it's my latest video. Is it still my latest video? I think I haven't uploaded anything since. Wait, let me check. It is still my latest video. You can go watch it after the stream if you missed the first half of the stream, because what we're tackling, the problem that we're tackling, is exactly the same. So yeah, basically projectile motion. Yes, it is still your video. Yeah. Basically, this is a projectile motion with linear air resistance. I'm gonna cook fried rice. I'm gonna leave. All right, have a good day. Enjoy your fried rice. Okay, so what we ended up doing was we found the case in which it's thrown directly upwards, and then we try to find the point where it's at the highest point, P rank every level. Are you talking about are you talking about ultra kill? Because if you're talking about ultra kill, I have, fun fact, I have P ranked every level, including, I think, yeah, it is ultra kill. Nice. I'm just here because I saw a thing on Discord. You said you were streaming, even though we're not Discord friends. That's nice. It's just free promotion. Let's go. Okay, so we try to find the position where Vy was 0, because that's where the peak of the projectile That's where the peak of the projectile is, which we found out to be where the peak turns out to be this expression right here. We're in the same server. Yeah, we do share a server. Or two. I think we share like 2 servers. Do we? I'll check that after the stream. But yeah, this is Y max. Alright. Alright, have a great day. Bye. So this term becomes V0 or VT. Boop. This is Y max. Now, too broke for article. Rip. That sucks. You could probably wait for like the Steam sale. I'm not quite sure when is it. Actually, when is the next Steam sale? I'm getting a little distracted. But Steam next Steam sale. Next Steam sale is the autumn sale, apparently. Ooh, it's like a whole month off. It's like an entire month. It's an entire month. You can wait that long, right? So if we are under the assumption that beta is very small, beta here, what is beta? Beta is the drag coefficient. So the bigger the beta, the more drag force there is. So if the beta is very small, if the value of beta is very small, it approaches 0, the Y max should be equal to, the value of Y max should be equal to the case of one without air resistance. No air resistance. Okay. So how do we do that? First of all, we are not going to consider these betas over here yet. We're going to consider the beta hidden in here. You see, Vt is the terminal velocity. And in my video and during this stream, we figured out that it is equal to G over beta. G over beta. Yeah. That means that means if beta is very small, very small, my handwriting is a little ass on this. I'm more acquainted with writing on a pen and paper, so that's that. If beta is very small, Vt is very large, which means that V naught over Vt is very small as well. Okay, so if beta is very small, so if it's on the order of like 0.00001 or something like that, then Vt, the terminal velocity, is going to be very large because there's not enough air drag to resist the object, so the object can fall much faster than if beta was smaller. Beta and alpha. Yep. We actually don't consider alpha here because I didn't name any variable alpha. Should I name one? I don't have any other variable to name alpha. Unfortunately, we can't have an alpha here. Except me, I'm sitting right here. Does that count? Alright, so here the terminal velocity is going to be very large, so obviously the ratio between the initial velocity to the terminal velocity is going to be very small. Because the terminal velocity is very large. Now, according to the question itself, I like the fact you didn't pay attention to the fact that you didn't see I spelled alpha wrong. I did consider that, but I did consider talking about that, but it doesn't matter. I understand, typos happen a lot. Hint, if the drag force is very small, the terminal speed is very big, so this value is very small. Now, there's this little trivia, this little very important line here. Use Taylor series for a log function to approximate natural log of 1 plus beta by 1 plus delta by delta minus 1 over 2 delta squared. So does this work? So what the fuck does this even mean? What does this sentence even mean? Yeah, Taylor series. The Taylor series is invented by Taylor Swift, you know, right? Someone could fact check that, but I'm pretty sure I'm right. Basically, what it's saying is that natural log of 1 plus x, shut the fuck up, I'm sorry. The natural log of 1 plus x is going to be approximately equal to x minus 1/2 x squared for very small x. So let me give an example. I'm just gonna go ahead and make it share my Desmos screen. There it is. I have it out immediately. I didn't actually intended it to, but never mind. Here we are. Now, as you can see, that if we can approximate the natural log function here, which is the red line. If the value of x is very small, so if it's like somewhere close from negative 0.1 or to 0.1, you can see. Why do I hear wood? I think it's just my aluminum foil, like being messed up by the fan. I'm in the I'm in my room, which has like it has like a quote unquote workshop thing. It's a makeshift workshop where I experiment with electric stuff. Like there's this taser that I made. No, not that. Oh, then maybe it could be I don't know. It could be the fact that the table is made of wood. I don't know. Are you done yet? You need to eat. Oh yeah, right. So this is this red line is the natural log of 1 plus x. So if we approximate it with this blue line right here, if the value of x is very small, yeah, do you move your computer a little bit? Yes, I did. It must have been that. You can see that if x is very small, or well, sufficiently small, you can see that they're practically the same line. The function of natural log x plus 1, or natural log of 1 plus x, and x minus x squared plus over 2, they're practically the same line. If you zoom out further, it diverges. But if you zoom in, it's pretty much the same. So that's why we can state that natural log of 1 plus x, it can be approximated by x minus 1/2 x squared. So therefore, y max is equal to v naught over beta minus vt over beta. And this natural log here, this expression, again, v naught over vt is very small. Like the movie. What movie are you talking about here? I'm not quite sure. We can rewrite this as v naught over vt subtracted by 1/2 v naught squared over vt squared. Line, the movie. Oh yeah, hold on, wait. Did that work? Okay, yeah, that works. That one Oppenheimer scene where the song plays. Can you hear the music, chat? Can you hear the music? I actually didn't have the music on. Not one. You guys can recommend me the music on stream for the stream if you guys want. Yeah, you guys can drop the. You guys can like type in the stream music if you want some music for upcoming streams. I'm gonna ship the copyright stuff, but yeah, if you want the music for the next streams or something. Also, what do you guys think of the thumbnail? Do you guys think I could make the thumbnail better or more eye-catching? And if so, what are your recommendations? I'm going to distribute that, so this one becomes 1/2 vt over beta. I'm distributing this term in here, so the negative becomes positive, and then we have vt over there, v naught squared over vt squared, which is going to be equal to, this one cancels out, so this term and this term cancels out. Now we're going to be left with 1/2 of v naught squared over beta vt squared. There's no vt squared there because t there cancels out, which means we are left with this. We are left with this equation. Copyright music it is. So vt is the terminal velocity, which is equal to g over beta, which means that this, I forgot to change the color. Which means this one becomes 1/2 times v naught squared divided by beta times g over beta, which gives us 1/2 v naught squared over g, which does in fact verify the fact that if beta is very small, if the air resistance is very small, then we can then the result of then the highest point would be approximately equal to the case where there's no air at all, which intuitively it makes perfect sense. Obviously, if there's no air, it should be approximately equal to when there's a little bit of air. So that's that. And this concludes our first question. For a little more on Taylor series, see problem 2.18. Should we do that? Nah, that's gonna be not gonna do that. 29.7. But we do have another problem, another question, which should be a little easier, or not. Actually, it might not be. Let me think. Okay, yeah, I'll be fine. I got this. Keep canvas signs. Paste that there, and now I kick a puck of mass m up an incline, angle of slope theta, with initial speed v naught. There is no friction between the puck and the incline, but there is air resistance with magnitude of that. Write down and solve Newton's second law for the puck's velocity. Motherfucker, I'm trying to edit and I hear the Windows thing and thought it was my PC. Oh, you want me to turn off, what is it? You want me to turn off the streamer mode and then just have my Discord just constantly I don't think I did the song. I don't think I did the sound right at all. Like the, Discord notification sound. You want that? Actually, I should turn it off for a moment. All right, guys, DM me something or someone. There we go. There it is. It's coming. All right, I'm gonna leave this on for like a few moments, and then I'm gonna turn it back on. For now, let's trying to catch up right now, but low-key system is dead. Nah, he'll be fine. Of course, Neon starts spamming me. All right, screw you. I'm turning streamer mode back on. Streamer mode activated. All right, shut up. System is low-key. Nah, he'll be fine. We got backups. Of course, Neon, you. Alright, so this is angle theta, and so we kick a puck of mass m up here with initial speed v naught. There's no friction. Obviously, there's going to be the gravitational acceleration of g. It was worth it. Fair enough. I suppose that's like not on the same level as that one time I infiltrated your stream by teleporting you out of that stream chat, out of that stream VC. Okay, so let's draw the free body diagram of the object. So the object's force, the pucks, right? The puck's gonna have the weight pulling it downwards like this. It has a force, and the force is going to be mg sine theta. And it's also going to be pulled back by the air resistance. F is equal to cv squared. Mg sine theta, you should probably know where this came from. This came from projecting the g along the two axes. This one's g, so this one's mg sine theta, this one's mg cos theta. So, but the one we're gonna care about is mg sine theta. So we can now set up our equation. F equals to ma. So I'm gonna say that the distance from down here up to this point. Okay, wait. The distance from here upwards, I'm gonna call it x, because it doesn't really tell us anything. So we know that, actually wait, do we need that? We just want the puck's velocity as a function of time on the upwards journey. So we don't really need the x. Okay, sorry. No. I don't even know what that word means. It probably doesn't mean anything. FU, man. Yeah. FU too. So mg sine theta minus cv squared is equal to mass times the acceleration, which is dv by dt. Guys, should we solve this in curved space-time? Would I be able to solve this in curved space-time? I don't think I have the time. Okay, whatever. So now this is yet again another differential equation that we can solve. this becomes what is it? This is gonna be 1 over, okay, it's gonna be negative, and it's gonna be mg sine theta plus cv squared. And this, there's gonna be an m up here. And this is gonna be dv. And we have to integrate that, and it's gonna be equal to dt. And we're gonna start off with v naught. This is gonna be t naught. This is gonna be starting from time equals 0. This is gonna be time equals something. This is gonna be v equals something. All right. So let's do that. Let me think. Because I forgot this integration thing. I could try to... Okay, here's what I'm gonna do. I'm gonna factor out mg sine theta and the m. So it'll be mg sine theta like this, and these are all and these are constants relative to v, so we can pull it out outside the integral. So now we're gonna end up with 1 over 1 plus c over mg sine theta v squared. This is dv. And the right hand side is simply just t. This one's, I actually forgot the integration thing. Wait, let me think. What does that integrate to? Was it an arctan? I think it was arctan. Wait. My apologies if I'm as silent as a mannequin. I'm not really as well knowledge fed, so I'm listening to it. Yeah, that's understandable. Just I just want to like explain my thought processes. Try my best to make people understand what I'm doing, at least a little bit. Like, don't expect like a full course worth of information, but like I want to give a little more insight as to how I be able to solve this question. So in case when you eventually encounter them, you may have like seen them before from somewhere. You might be able to solve them with a little bit more ease. My dumbass cannot know shit. My intellect will diffuse into you. Okay. I think this becomes tan. Let me try. Integrate. I genuinely don't remember the values. Now, can you answer my homework about circuits? Sure. DM me, and I got you covered. No promises that I'll answer immediately though, because I might be a little busy, but I'm desperate. Alright, yeah. No promises that I'll answer like immediately. But yeah, it is the same thing. So we can now say, we can claim that so we have the fact that integrating 1 over 1 plus x squared dx is equal to arctan plus plus the integration constant c. Alright, so now I have to find a way to put this into the into words into this form. I have to find a way to find x, to turn this thing into x, which is simple enough, I guess. Actually, I could cancel out the m there, so it becomes 1 over g sine theta. And so now we know that if we let x, I'm going to let x be equal to square root of c over mg sine theta times v. Then a small change in x, dx, must be equal to this whole thing times this small change in v. You know, it makes sense, right? If I change v a little bit, then x is going to change by whatever v changed by times the scale that we scaled it in front. So if v increases by 1, x is going to be increased by this factor over here. If v increases by 2, then x is going to be increased by 2 times this guy. So dx equals to this thing times dv. And so this dv here is pretty much the same thing. It's a small increment in v. So this technique is known as U substitution. I'm certain you've heard of it if you've taken calculus before. And this becomes dx. But dv is not directly equal to dx because we're going to have to multiply it by square root mg sine theta divided by c. And these things are constant, so we can kind of just pull it out of the integral. So and it can cancel with this guy. So we're gonna have square root of m over cg sine theta, and then we're going to be left with the integral of 1 plus x squared dx, and this is going to be x starting from x naught to x. We'll plug in x naught and x later on, just not right now, because once we perform the integration, we're going to end up with an arctan function. That is, it's going to be arctan of x minus arctan of x naught equals to t. Okay, now what? Now we want to find the velocity as a function of t. I'm going to unpack x. Because before this, we packed this whole expression into x. We packed this whole expression into x so that we were able to integrate it. We were able to integrate this whole thing much more easily. So what I'm going to do is I'm going to unpack it. That's personally how I view integration with using U substitution. I normally just call it like creating a zip file and then doing the integration with that zip file and then unzipping it after you finish the integration. That's how I personally view it. I think it's pretty neat, I guess. So now we're going to have arctan of square root c over mg sine theta v minus arctan of this exact same thing. So I'm just gonna Control C, Control V. It's not even a good copy paste, but it works. And that's all that. That's all that matters. So I'm gonna turn this into V naught because this is where X naught is. So it should correspond to V naught. And it's equal. Why did I set it to be equal to 0? It should be equals. It should be equal to t. And now, obviously, what I do next is just write the whole thing again. Arctan. Why am I writing the whole thing again? I just like literally copy pasted it. Arctan here is going to be equal to this expression. I'm gonna multiply both sides by the inverse. I'm gonna divide both sides by this expression, which should give me square root of cg sine theta over m. Multiply that by time. Yeah, and then I add arctan of this constant, mg sine theta v naught. Boop, boop. And so we can now find the value v at any point in time by taking the tan. Arctan is the inverse of tan, right? So if I take the tan, so if I apply the tan function to the entire equation, the left-hand side is gonna undo the arctan. Whereas on the right-hand side, it's just gonna apply tan to the entire fucking expression. I would use the tan addition formula. Like there's a formula for tan a plus b, but I'm too lazy to look it up, and it probably would just make it a big mess. So I'm not gonna do that. And so now we know that v equals to that thing. I should remove that and then multiply the right hand side by that. By the inverse of that. Give me a sec. So this side becomes square root of mg sine theta divided by c, and this is what the value of v is as a function of time. Alright, so that was basically just an integration task by, separating the variables. And we now have the value, and now we have the velocity of the object as a function of time. Okay. Alright. And we're not done, obviously. We got this part done. Write down and solve Newton's second law for the puck's velocity as a function of t on the upwards journey. Simple enough. Well, yeah, on the upwards journey. Alright. But we're not done. Obviously, there's the how long does the upward journey last? So, I know exactly how to do this. It's simple. So let's just get it done, and that should be it for our stream today. A little faster, I think. The stream was an hour and a half long, which is half of what we had in other streams. So that's like pretty good, I think. All right, yeah. Let's do that. Yeah, the last stream was like, holy hell, last stream was 3 hours. That's insane. Okay, eat. I will, I assure you. Let me just finish this one final question. That is, I'm going to copy that first. Copy, paste. The last question is, at what time does it take to stop? Also, truth be told, I don't think Roku's going to kill this. Obviously, he's not. He's not going to kill off the main character like that. Our fandom will not be happy. We're going to execute. We're gonna crucify him, bro. So we need to find a time where we need to find a time of the upwards motion. So obviously, when you have this air resistance, it's gonna go up, and then that's gonna be where the timer ends, and then it's gonna start going down. So when it goes up and then it starts going down, it means that the velocity here is equal to 0. Think of this triangle as a right triangle. So this is v naught, yeah. So this is v naught. This is where v equals 0. Yeah, I think I know what you meant now, Neon, by the wood sound. I think I kicked the table. I think that's what happened. So 0 equals to square root of mg sine theta over c times tan of arctan square root c over mg sine theta. I forgot a theta here. V naught minus square root of cg sine theta over m times t. And this expression has to be equal to 0. We know for a fact that this expression is definitely not going to be 0. So I'm going to say that, so this one doesn't really fucking matter. Why am I saying fucking a lot? So it means that tan of this whole thing the tan value of mg of arctan c square root c over mg sine theta v naught minus square root of cg sine theta divided by m. Why is the m over here again? Wait, they do that right. Why is m on a different level? Where did that come from? Where did that come from? That comes from here, which came from here. Okay, yeah, okay, that makes sense. That makes sense. Maybe 4 and 6 over. No, get that guy out of here. All right, and this is t, and this is equal to 0. So for this expression to be equal to 0, this expression must be equal to 0. And the only case where tan of something is equal to 0, actually it's not the only case. It's not the only case, but the simplest case is when tan... Well, I'm not even here for this complicated stuff. I'm just here to support you. Thank you. This tan function is going to be 0 if it is 0. Okay, tan of x is equal to 0 for when x equals 0, or if it's equal to 2 pi. No, wait, not just 2 pi. I think it's pi as well. Wait. Yeah. When x equals 0, x equals pi, x equals to 2 pi, etc. So that means for x equals to n pi for any n, for any value of n. For any integer n. Okay. So let's consider the simplest case first, where n equals 0. So that means that arctan square root c over mg sine theta times v naught minus square root of cg sine theta. It's a stretch for me to cope with my mother doing listening. Ah, damn. It would be kind of a pain. You don't need to like stay tuned. Actually, I might as well just make the what's it? I might as well make a playlist like right after the stream. I'm gonna make like a playlist for all of my homework stream if you ever want to like go rewatch them. It's RGX2 there. Okay, stop. All right. So that means arctan of this thing, mg sine theta v naught, is going to be equal to square root of cg sine theta over m times t. Therefore, t, the time during the upwards motion, is equal to, for m over cg sine theta times arctan square root c over mg sine theta v naught. And that is our answer to the question. This is how long it's going to take for the puck to go up and then start coming back down. So let's prove that. By that I mean I'm going to create a simulation. I'm going to create a simulation for such example. So I'm going to define the variable for the system first. We're going to first have theta. I'm going to call it theta not because it doesn't allow me to use theta as a function, as a variable. So theta equals 0.2, which means that we can write this as y equals to tan theta naught x. And this angle right here is going to be 0.2. If theta equals to 1.5, the angle is going to be like that. So yeah, this works. This is going to be our, what's it? This is going to be our slope. To be more precise, I should do that. So now we have our slope line, sloped plane. Next up, next variable, what should we set it to? I'm going to call it S for, I don't know, displacement. And I'm going to use it as Sn and Sm. Sn is the current text and Sm is the previous text. Sn can honestly just be anything. I'm going to, of course, have set S. Actually, no. I'm going to use, what do I do now? G equals to 9.8. And C equals to, what should we have? What should we set it be? C equals to, I'm going to put it to 0.1. And then I'm going to set the mass of the object. Actually, does mass matter? Mass does matter. I'm going to set the mass object to 1 kilogram. And then I'm going to set, what else? I'm going to set the initial velocity to 1. Okay. And then I'm going to have the another folder called the updater. Right now we're so for those who just recently joined, we're checking our answer. We're checking our answer by making a simulation in desmos.com. Updater, I'm going to have the action called I'm going to have the action A1 be an act of Sn, setting the value of Sn to be, and this is called a Verlet integration technique. It's more precise than Euler. Okay, so what we're doing right now is, this is called a Verlet integration. Sorry for disturbing the stream, but do you know Dexter, like the TV show? I've heard of it. I haven't watched it, but I've seen a lot of memes from it. I don't know where I can watch it actually. If I do have the time to watch it and the motivation to, because I keep procrastinating on watching anything. Well, does this, okay. I'm going to call this dt. So we're going to have these things. Verlet integration updater. We're going to have Sn equals to 1 or something, Sm equals to 1 first. Okay, and dt, this is going to be our time. So I'm going to set it to like 0.1. So let me explain what this whole thing means first. The action A here, the action A1 here is going to set the value of Sn, which is the position of the object in the upcoming frame, to be equal to, give me a moment, to be equal to itself plus the velocity times the tick, times dt. And this is actually, and this is the velocity from the this expression is, hold on. Sn minus Sm here is the distance, is the small, no, it's the delta x. dt is the delta t. So this whole expression becomes v, the velocity at this certain point. And then if we want to find the velocity, and if we want to find where Sn moves, we're going to have to multiply the velocity, the current velocity, by the time, dt, which cancels the dt out. So we're going to end up, with 2Sn minus Sm. This is from Verlet integration. And then we also have the term for a. A here is a function of, a here is going to be the function of v, which is going to be equal to negative cv squared. Wait. Give me a moment. It's going to be negative sine of v times cv squared. What this means is if v is positive, then this acceleration, this drag force, is going to be pulling it down. And if v is going downwards, then the acceleration is going to be pushing it up. This term is from the air resistance. And of course, there's going to be the gravitational acceleration term, which is going to be the gravitational acceleration along the what's it called? Along the tangent, along the slope, along the inclined plane. Yeah, inclined plane. Give me a moment. If you want to see more, if you want to see what I'm doing with this simulation, you can search up Verlet integration. All right. Let me go check the variables real quick. It's actually going to be c over m here. And I think that's our acceleration. And this acceleration is going to affect the simulation. We multiply by dt. So now we have acceleration. This whole term means the acceleration at this velocity. And then we multiply by the time step squared. I'm pretty sure I have the formula correct, I think. And A2 is we're going to be setting the previous velocity, the previous position, to be the current position, Sn. So these two is going to give us the value of, these two are going to tell us where we are. It's going to be updating constantly. And now we're going to set t equals dt, t plus dt. I'm going to set initially t equals 0. This one just keeps track of the time, what time it currently is. So now we have this set up. I'm going to close that thing. This is not the variable. I should also put in like visual. All right, and then I put that there. I can hear a laptop fan in the background. It's actually not the laptop fan. It's actually like the fan that's actually blowing into me right now, because I don't have an air conditioner set up in this room yet. Because my air conditioner, well, it's kind of, it doesn't look good right now. Yeah, it very much doesn't. Okay, and this is our this is gonna be our puck thing. I'm gonna make it a little bigger, make it like, I don't know, 20, and I'm gonna not make it draggable because it would be a pain. Okay, it's gonna have a size of 20 pixels, and that should work. Yeah. And now I have the universal action, which is gonna be just A1, A2, A3, which means I can now add the ticker which is going to be the action. It's going to run this action. It's going to run these actions every tick. So I'm going to set this whole thing to 0 first. And then I'm going to have, I got a bath, dude. Alright, have a great bath session. I probably will be here, still be here, I think. I'm gonna make the resetter. This is gonna be R, the universal resetter, R1, R2, and R3. R1 is gonna be, bye-bye, have fun studying and eat. I will. I assure you, I will. I won't. This one is gonna set Sn to be equal to 0. No, actually no, not Sn. Sm is gonna be set to 0. R2 is gonna be setting Sn to be equal to Sm, no, equals 0 plus the initial velocity times dt plus 1/2 a of initial velocity times dt squared. And that should get us whatever we have. And then R3 is going to be setting the value of time to 0. And if I set all of that, it should be, yeah. The simulation should be ready to be run. And now I hit run, and it goes down immediately. Okay, well, that was not what I expected to happen. I'm also going to make this in real time. So if I run that, it's going to be going like that. This one will run at exactly real time as long as d isn't too small. If d is too small, then it's gonna try to run the simulation too quickly, and it's gonna crash. Not really crash. It's gonna lag. And if it lags, then it's gonna be a pain. Yeah. I'm gonna. What do I set theta to be equal to like 0? What happens when we do that? Wait. Reset. Yep. Okay. I think I got the formulas right. Wait. Verlet integration. Verlet integration is a numerical method used to integrate Newton's equations of motion. Yeah, I'm aware of that. First, we set that. Okay, yeah, that is correct. It is indeed correct. So now I'm going to run this. It should go on there. It should go on almost to infinity. It is going to go off almost to infinity. But you can see that it's slowed down. It slowed down a little bit because of the fact that there is air resistance acting on the object. So right now it's kind of slowing down. But it can still go on indefinitely. Okay, let's reset. And let's say d equals to something like 5. I'm gonna make it a little more sloped, and I'm gonna make the initial velocity quite high. Ah yes, Gojo physics. Gojo physics. Have I done that? Have I done the Gojo physics thing? I don't think I have the Gojo physics set up. Yeah, I don't think I haven't done that. But I do have, your favorite drink. My favorite drink. Smoothies. I like smoothies, like especially strawberry smoothies. I really like strawberry. Yeah, I think that's that. Yeah, I think I like that. I like that a lot. Okay, let's say if c equals 0. If c equals 0, it means that this object is going to be going on without the. You need the sugar-coated one too. Yeah. This doesn't. Yeah. Okay. So now we have c equals 0, which means that it should be moving around with no air resistance. So if I run that, it's going to be going up there, and then it's going to come back down. And it goes down, 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 down you go. No way to stop. So what I'm going to do is I'm going to try to pause it at exactly... Okay, so from our solving, we got that the time it takes from downwards to up, from going down to up, from like, you know, the upwards trip. The upwards trip is going to have this time. This is the time it's going to take. So I'm going to type that out. I'm going to write square root of m over cg sine theta, m over cg sine theta naught, and it's undefined because I set c to be 0, right? Well, it'll be defined soon. Give me a sec. Square root of c over mg sine theta naught, and then I multiply that by v naught. Did I forget something? No, I didn't. Okay. It's undefined. Let me just set the c to be something that's not 0. Alright. Set something to not be 0, and it says that the time is gonna take to get up to the highest point is gonna be 0.938. So I'm gonna run that, and I'm gonna try to pause at exactly that time. I'm gonna slow the simulation down significantly as well, so I could you know, catch it in time. Whoop. Pause. Alright, let's see. What is the time right now? What is the time? 0.925, which is close enough to 0.938. So that's nice for our instance. Let's say if we take it a little more to the extreme. If I set g to be a little smaller, what would happen? If I set g to be a little smaller, if I set c to be a little smaller, we're gonna have like something like 4.1. I'm gonna change the simulation time back to normal. Initial velocity should be good. Reset everything. I forgot reset should have double 2 T's. And yeah. And now if I run and then I pause the moment that it reaches the highest point, we should get something along the line of 4.1. Anyway, proceed to do that. And I forgot to click. Okay, it did click, but like my mouse actually does double click thing. My mouse tends to double click, so it probably like stopped and then it double clicked and continued. So let's do that again, and we should get 4.1. Let me just 4.475. That's because I had a little bit of a delay between pausing it and, you know, actually making it work. Yeah. So yeah, I'd say this works. The number isn't precise mainly because of, one, the fact that it's a simulation, it has discrete time steps, and two, the fact that I suck at timing. So I'm going to save this. I'm going to call this the incline plane simulation, and I'm going to save that. Also, there's this pendulum simulation that I did from the previous stream. I want to mention before I end off the stream, because I finished all of the problems today. This is the pendulum simulation. We have two things. We have the Euler method, which I did last time. Basically, just keeping track of v, keeping track of the value of theta, and then continuously updating each of them, which is the naive approach. But then we have the Verlet integration, which was the approach that we just did, which is much more precise, and I'm going to show you how precise it is. By first resetting it, and you're going to see that I think I set the green one, the visual, yeah, the green one is Euler. The green one is the Euler method, and the blue one is going to be the simulation run by using the Verlet integration method. If I run this, you can see that the blue one actually does oscillate around at the same height. It's like in real life, it would still oscillate around at the same height. But then you can see that the green one kind of just goes a little crazy, and it just starts spinning uncontrollably, which kind of defies the law of physics because it should have conserved energy in our case. So this green one is, again, you're using the Euler method. You can see that the energy from the Euler method right now is at 32. The total energy is at 32 joules or something. But the initial energy should have been somewhere like -5. So you can see that Euler integration is not the best. So I started using the Verlet integration technique. It's kind of satisfying, I gotta say. How to hypnotize a physicist? True. True, this would work. This would work on me. Alright, I'm gonna close this so we can see just the Verlet integration thing in action. So you can see that this one does indeed goes up and down like that. And this is from the previous stream as well. This is when I calculated the period of the oscillation. Here you can see that the period of the oscillation, I set it to be calculated by using the formula that we got. It turns out to be 2.140 something something something. And we're going to prove that by using the simulation. Okay, gotta go. Gotta eat dinner chicken curry with rice. Oh, nice. That sounds really nice. I like chicken curry. Actually, wait. Unless we're talking, I like the Japanese version of the curry more than yeah. They are really nice. It is really nice. All right, so this is the period of each swing should be 2.14 seconds, and I have this timer right here, t equals 0 initially. And I'm going to test that if this formula is true or not by running the simulation and going to keep track of on the 10th swing. I'm going to pause and I'm going to check the timer. And we divide the time by 10, we should get the period of the oscillation. So let's do that. 1, 2, 3, 4, 5, 7, 6, 8, 9, 10. Okay, so that was 21.4 seconds for 10 oscillations. So for 10 oscillations, it took that much. So if we divide by 10, we can see that the time it takes is 2.14 per oscillation, which lines up perfectly with our calculated result prior. So yeah, this is just updating my previous. I thought that was my professor counting. I totally did not just miss count 5 and then I went to 7. I totally did not do that. How much did I miss? You missed the entire stream. Anyway, so yeah, that let's test it one more time with a different initial setup. I'm gonna push it a little bit to the extreme here. I can put it all the way up here, and I'm gonna reset. And here's and what we're gonna see is that each oscillation should take around 4 seconds. And I'm gonna keep track of. I'm gonna be counting to 10 swings, and I'm gonna divide the time by 10, and we should be getting some value that's close to 3.98. So here we go. The first swing we get 1, 2. Okay, don't worry about it. There's still some other streams that you can catch on. 4 that you can catch up on. Yeah. 5. Like 6. I intend to like stream every time I get my homework. So you probably shouldn't be. You probably would be able to catch up on most of my streams anyway. All right. 9 and 10. So the time we got for 10 swings was 39.85. Divide that by 10, we get that each swing took 3.985, which is almost exactly what we calculated. So that is perfect. The simulation is actually very fucking good. And the formula that we got was actually correct. So overall, I think that Desmos, you can learn how to build simulations so you could actually like check your answers. So like the answers that we got here from the question that I did earlier can also be proven. That's such a fun swing and totally safe for kids to play. I know, right? So yeah, what I'm saying is, if you ever have a problem like this, especially in classical mechanics, you can try to like implement the system itself on Desmos or some other simulation app. Desmos itself isn't even a simulation app. I just use it for simulations, and it works. So if you ever need to check if some variable is true, then trying to use Desmos to make a simulation out of it. So yeah, that was a fun stream. The problems weren't too difficult. Anyway, I fell face first into asphalt and got a boo-boo on my knee and palm. Can you kiss it? No. Alright, so that was a great stream. It's nice because most of the problems I've seen before from my projectile motion video. Again, I'm a total sellout. Go watch that video. My latest video. All right, yeah, it is a good stream. My latest video, which talks about projectile with air resistance, which is exactly which is what this entire question was all about. Projectile motion with air resistance. So yeah, have a great day. Just study well. I hope you guys study well. I hope you guys have a fun time studying. Nice stream, thank you. So yeah, I'll be ending the stream now. I have a few other homework to catch up on. It's mainly like, it's not really a problem homework. It's more like making a poster or some infographics or some essay. Those are kind of boring to deal with, so I'm not gonna stream them, obviously. But here, that is it. This has been a great stream. Have a good day, y'all. See you guys next stream. Or next video, if I do upload it first before my next homework. Yeah, whatever. See you guys.